Network analysis. Network analysis is a vital technique in operations research, or used for planning, managing, and optimizing complex projects and systems. It involves representing problems as a network of interconnected activities or tasks and analyzing them to improve efficiency. This approach is widely used in project management, transportation, logistics, and supply chain optimization. Network analysis helps organizations minimize project completion time, allocate resources effectively, and identify critical tasks that influence overall efficiency. Network analysis is a mathematical and graphical representation of interrelated activities in a system. It involves constructing a network diagram consisting of nodes, events, and edges, activities, to model dependencies and constraints within a project. By analyzing these networks, decision-makers can determine the most efficient way to execute tasks, identify critical paths, and optimize resource utilization. Network analysis is based on graph theory, where a system is represented as a network of nodes, representing tasks or events, and arcs, representing dependencies or relationships. Two primary techniques used in network analysis are: network analysis is the synthesis of two most useful techniques of project management, I.E.P.E.R.T and CPM. PERT was developed as a management tool for coordination and early completion of Polaris ballistic missile project in U.S.A, resulting in reduction of 30% time in project execution. A contemporary of PERT is CPM and was developed in connection with maintenance and construction work. Both the techniques use, PERT and CPM use network and critical path as the basic tool of project management, and both are very helpful in completing a project on schedule by coordinating different jobs involved in this completion. Critical path method, CPM, used for deterministic project scheduling. CPM identifies the longest path of dependent tasks in a project, determining the minimum time required for completion. It helps in resource allocation and project planning. Program evaluation and review technique, PERT, used for probabilistic project scheduling. PERT incorporates uncertainty by considering multiple time estimates for each activity, optimistic, pessimistic, and most likely. It helps in estimating the probability of completing a project within a specified time frame. A graphical presentation or an arrow diagram presented to the management in respect of a project, which consists of all details regarding consumption of time and cost, not only for each activity but also for the whole project, so that management can manipulate the resources and cost can be controlled in a more effective manner. Network analysis is a successful technique frequently used to plan, monitor, and control the projects involving thousands of activities. 1. To minimize project cost. 2. To minimize the project time. 3. To ensure optimum utilization of human and other resources. 4. To ensure minimum conflicts and unnecessary delays. Activity. An activity refers to the physically identifiable part of the project which consumes time and cost. An activity is represented by an arrow. The activity may have a predecessor activity and a successor activity. E.g., lay pipeline is an activity. E.g., 1. Activity should be represented by an arrow connecting two nodes. 2. All activities should be in forward direction. It may be upward or downward direction, but it can never be in reverse direction. 3. Activities should be either represented by numbers or alphabet. 4. All alphabets and NOS should be in ascending order. Event. Sequence of activities for house construction project. Network diagram representing house construction project. The network diagram in the above figure shows the procedure relationship between the activities. Activity A, preparation of house plan, has a start event 1 as well as an ending event 2. Activity B, construction of house, begins at event 2 and ends at event 3. The activity B cannot start until activity A has been completed. Activities C and D cannot begin until activity B has been completed, but they can be performed simultaneously. Similarly, activities E and F can start only after completion of activities C and D respectively. Both activities E and F finish at the end of event 6. Network techniques. Government and industrial establishments always plan new project for future development and expansion. A project is a collection of well-defined tasks called activities, and when all these activities are carried out, the project is said to be completed. Many projects are of great size and complexity and require huge expenditure and time, e.g. construction of bridge. Thus, there is a need of careful study and analysis of the entire project. There are many techniques to study and analyze such projects, and the main object of all such techniques is to find some strategy so that project finishes in time with lowest cost. Network techniques help the management in planning the complicated projects, controlling working plan, and also keeping the plan up to date. Network techniques help the management in reaching the goal with minimum time and least cost. Network techniques have resulted in better managerial control, better utilization of resources, and better decision making. Network techniques have resulted in saving of time or early completion of the project, which in turn results in early return of revenue and increase in profit. A graph drawn connecting the various activities and events of a project is a network diagram. Each event is represented in it by a circle, called node, and each activity by an arrow. The arrow denotes the sequence of activities. Dummy activity: an activity which doesn't consume any time and productive time and cost. It should be represented by dotted line but not by any alphabet. It should be introduced to maintain preceding and succeeding relation. It is represented by dotted arrow. Network diagrams are of two types. 1. Event-oriented diagrams, PERT. 2. Activity-oriented diagrams, CPM. Anyway, a network, whether event-oriented or activity-oriented, will include both events and activities. Each activity is represented by one and only one arrow in the network. No two activities can be identified by the same head and tail events. Except for the nodes at the beginning and at the end, every node must have at least one activity preceding it and at least one following it. Only one activity may connect any two nodes. Activity time, days. 1 to 2 2. 1 to 3 4. 1 to 4 3. 2 to 5 1. 3 to 5 6. 4 to 6 5. 5 to 6 7. 7. 5. 7. 1. 7. 5. 1. 3. Construct a network for a project whose activities and their predecessor relationship is represented in the following table. K. K. Draw a network diagram to the following set of activities. Critical path analysis is a special application of network analysis. It uses network analysis for scheduling production, construction projects as well as research and development activities. Besides this, it is used in certain other situations that require estimates of time and performance. The critical path is the overall time it will take to complete the project. It is the longest path in time through the network. Draw a network diagram. Find the earliest event time, TE, and latest event time, TL, of each event and show in network diagram. Calculate earliest start time, earliest finish time, latest start time and latest finish time for each activity. Determine float for each activity. Identify critical activities, having zero floats. Draw double line in the network diagram passing through critical activities. The double line shows the critical path. Calculate the total project duration, which is the sum of durations of critical activities. Before critical path in a network is determined, it is necessary to find the earliest and latest time of each event to know the earliest expected time, TE, at which the activities originating from the event can be started, and to know the latest allowable time, TL, at which activities terminating at the event can be completed. E1 equals 0. 2. Earliest occurrence of an event when there is only one immediate predecessor activity equals earliest occurrence of predecessor event plus duration of the predecessor activity. 4.2. E.g., E1 equals 0. E2 equals 0 plus 4 equals 4. E3 equals E2 plus duration of 2 to 3 equals 4 plus 2 equals 6. 3. 9. 3. Latest occurrence of an event when there are many successor activities equals minimum chosen from latest occurrences of all the successor events duration of each corresponding successor activity. E.g., L5 equals min, L6 duration of n, L7 duration of n. EST of an activity equals earliest of its tail event. LFT of an activity equals latest occurrence of the head event of that activity. EFT of an activity equals EST of the activity plus activity duration. LST of an activity equals LFT of the activity, activity duration. Float equals LST. Activity time. 1 to 2 4. 1 to 3 1. 2 to 4 1. 3 to 4 1. 3 to 5 6. 4 to 9 5. 5 to 6 4. 5 to 7 8. 6 to 8 1. 7 to 8 2. 8 to 10 5. 9 to 10 7. Construct network diagram. Compute TE and TL for each event. Find EST, LST, EFT, LFT values of each activity. Find critical path and project duration. Computation of TE values for the events 1 to 10. E1 equals 0. E2 equals E1 plus duration of 1-2 equals 0 plus 4 equals 4. E3 equals E1 plus duration of 1-3 equals 0 plus 1 equals 1. E4 equals maximum of E2 plus duration of 2 to 4 and E3 plus duration of 3 to 4. Equals 4 plus 1, 1 plus 1, equals max, 5, 2, equals 5. E5 equals E3 plus duration equals 1 plus 6 equals 7. E6 equals E5 plus duration equals 7 plus 4 equals 11. E7 equals E5 plus duration equals 7 plus 8 equals 15. E8 equals max, E7 plus duration, E6 plus duration, equals, 15 plus 2, 11 plus 1, equals 17, 12, equals 17. E9 equals E4 plus duration equals 5 plus 5 equals 10. E10 equals max, E8 plus duration, E9 plus duration, equals 22, 17, equals 22. Computation of TL values for the events 1 to 10. L10 equals E10 equals 22. L9 equals L10 duration equals 22-7 equals 15. L8 equals L10 duration equals 22-5 equals 17. L7 equals L8 duration equals 17-2 equals 15. L6 equals L8 duration equals 17-1 equals 16. L5 equals min, L6 duration L7 duration, equals, 12, 7, equals 7. L4 equals 10. L3 equals 1. L2 equals 9. L1 equals 0. Five. Construct network diagram and compute critical path and its duration. E1 equals 0. E2 equals 2. E3 equals 2. E4 equals 1. E5 equals 6. E6 equals 10. E7 equals 7. E8 equals 11. E9 equals 15. Computation of TL values. L9 equals 15. L8 equals 12. L7 equals 8. L6 equals 10. L5 equals 11. L4 equals 7. L3 equals 2. L2 equals 7. L1 equals 0. Critical path 1-3-6-9. Project duration equals 2 plus 8 plus 5 equals 15. PERT system is preferred for those projects or operations which are of non-repetitive nature, or for those projects in which precise time determination for various activities cannot be made. In such projects, management cannot be guided by the past experience. For example, the project launching a spacecraft involves the work never done before. For such research and development projects, the time estimates made for use may be little more than guesses. PERT system is best suited for such projects. Time estimates. Identify the events and activities and prepare a suitable network diagram. Events are numbered in ascending order from left to right. Obtain the various time estimates for each activity. They are optimistic time, 2, pessimistic time, TP, and the most likely time, TM. Compute the expected time, TE, for each activity. Compute the float associated with each activity. Determine the critical path. Find the total expected duration time by adding the time estimates for various activities on the critical path. For a project given below, find expected time for each activity, TE and TL values for all events, EST, FLST, and LFT values for all activities. Critical path. Solution. Computation of TL values. L8 equals 37. L7 equals 28. L6 equals 29. L5 equals 22. L4 equals 13. L3 equals 15. L2 equals 5. L1 equals 0. Critical path equals 1-2-3-5-7-8. Total duration equals 37.